All right, as we continue on in chapter 8, I just want to define a couple of terms for you. Molecular formula versus empirical formula for a compound. And what we've been used to using is the molecular formula. That's what we've seen so far. But I'm going to look at the molecular formula of glucose just to distinguish the difference between the molecular and the empirical formula. The empirical formula for glucose looks like, the molecular formula for glucose looks like this: C6H12O6. 6 carbons, 12 hydrogens, 6 oxygen atoms, right? But if we want to know just the ratio of atoms to one another in the formula for a particular compound, what we're going to do is, that means we need, if the numbers that are out to the right of each element, if those numbers are all divisible by a number other than 1, we can reduce those numbers down. So we see that this has a 6, a 12, and then a 6. All three of those numbers are divisible by 6. And if we divide each of them by 6, we get C. So in other words, we're going to do 6 divided by 6, H, 12 divided by 6, O, 6 divided by 6, right? And so that's going to equal CH2O when we do that, right? And so that's what we call the empirical formula. That is the simple ratio of elements to one another, right? Basically, we have twice as many H's. The empirical formula tells us we have twice as many hydrogen atoms in this compound as we have carbon and oxygen atoms, right? Now, the actual molecule looks like this, right? Has 6 C's, 12 H's, 6 O's. But the ratio between those elements is, for every 1 C, there's 2 H's and there's 1 O. Okay? So that's the difference between molecular versus empirical formula. Now, sometimes a compound's molecular formula is its empirical formula, right? For example, with H2O. We can't simplify that any further. So that is both the molecular and the empirical formula for water. Also, ionic compounds, they're always already in their empirical formula. And there's a picture on page 234 that shows you the way that ionic compounds bind together. See how they're all clumped up, and there's just a row of ions there as they're held together by that magnetic charge. So they don't look the same as the covalent compounds look, like like water that we have in the picture to the right of that. And so anyway, they're always written in their simplest form. That they've been reduced down to the simple ratio of ions to one another. Let's look at example 8.2 just real quick and try this again. C8. So example 8.2 says, what's the empirical formula, not C18, for C8 and H12O4. Again, we ask ourselves, first of all, is this the empirical formula? It could be, but how do we check to see if it is? Well, we see, are these three numbers here divisible by any number other than 1? And they are. They're all divisible by 4. So the empirical formula then for this guy would be C2, because 8 divided by 4 is 2, H3, because 12 divided by 4 is 3, and then O, right? So this is the empirical, whereas this is the molecular. Okay? That was the first question in 8.2. Actually, the first question was, is this the empirical or the molecular formula? And we would say it is the molecular, because all of the numbers are divisible by another number. And then the second half of the question did ask us, give the empirical formula, and we did. There's one other part to 8.2, and it gives us the empirical formula of a compound, right? This time it doesn't give us the molecular, it gives us the empirical formula, and it says the empirical formula of a compound is CH5N. All right, we know that's the empirical. We know that's not actually what the molecule looks like. They do tell us, though, that the molecule has a molar mass of 93.21 grams. 93.21 grams. That's the actual molar mass of this molecule. Okay? So they want us to give the empirical formula. How would we figure that out? Well, we know that this is not the molecular formula. And I don't know, I may have said empirical when I needed to say molecular a minute ago. We're trying to find the molecular formula, right? If I go to my periodic table and I look at what the molar mass would be for the compound if this was its molecular formula, right? I would see that I would go and look at carbon and see that carbon has an atomic mass of 12.01 and hydrogen of 1.01 and nitrogen of 14.01. And so I would say, well, I've got one carbon, that's 12.01, plus 5 hydrogens, 5 times 1.01, plus nitrogen, which is 14.01. And I would add all of that up, and when I add it all up, what do I get? I get a value of 31.07 AMU, right? Based on the periodic table, this is the atomic mass of this compound, which is the empirical formula of the actual compound that we're looking for, all right? Notice this is not the same as this, just like we would expect to be the case, right? Because this is not the molecular formula. Well, if this was the molecular formula, this would mean that 1 mole of this stuff has a mass of 31.07 grams, right? But the actual molecule has a molar mass of 93.21 grams. So if we take this and we divide it by what the molar mass would be of this substance, then we get a value of 3, right? The actual molecule has a molar mass that's 3 times greater than this. So what does that mean? It means that our molecular formula is going to be the little numbers that are out next to each of these times 3. In other words, we have 3 times more atoms than what this one shows. So we got to do 1 times 3, H is 5 times 3, and N is 1 times 3. So the molecular formula for this substance is C3, H15, N3, and that would be our final answer. All right, so molecular versus empirical. Empirical is the simple ratio of all of the atoms to one another, all of the elements to one another in the molecule. The molecular formula is actually how many atoms are in that molecule, okay?